In this video, we're going to look at a second garbage collection technique, stop and copy. In stop and copy garbage collection, memory is organized into two areas. We have an old space that's used for allocation, and so all of the data that the program is currently using lives in this area called the old space. And then there's a new space, which is reserved for the garbage collector. And so this is not used by the program. This is just for the GC. And so the first decision in stop and copy garbage collection is that the program can only use half the space. And there are some techniques, more advanced techniques for stop and copy garbage collection that allow the program to use more than half the space. So this isn't as bad as it sounds, but fundamentally, a fairly significant fraction of the space has to be reserved for the garbage collector. Now, the way allocation works is that there's a heap pointer here in the old space, and everything to the left of the heap pointer is currently in use. This is where all the objects have already been allocated in this area that I just shaded here in red. And then when it comes time to allocate a new object, we simply allocate it at the heap pointer. So the heap pointer will simply bump up, and some block of space will be allocated to the next object that we want to do. And it'll just keep marching through the old space, allocating as you allocate more objects. Okay, so allocation just advances the heap pointer, so one of the advantages actually of stop and copy is a very simple and fast allocation strategy. Now, eventually, of course, if we allocate over and over again, we're going to fill up the old space, and so a garbage collection will start, GC will start when the old space is full. And what is it going to do? It's going to copy all of the reachable objects from the old space into the new space. And the beauty of this idea is that when you copy the reachable objects, the garbage is left behind. So you simply pick up all the data that you're using, you move it over to the new space, and all the junk that you didn't need anymore is left behind in the old space. And then after you've copied stuff to the new space, first of all, since you left the garbage behind, you're using less space than you did before the collection, so there's some space available now in the new space for allocating new objects, and then you simply swap the roles of the old and new space. So the old and new spaces are reversed, what was old becomes the new, and what was new becomes the old, and then the program resumes. So let's take a look at a quick example here just to get the idea of how this works. Let's say we have our old space over here. This is the old space. And we have one root, which is this object A. And so what are we going to do? Well, we're going to make a copy of all the objects reachable from A, and we're going to move them over to the new space. And what's that going to look like? Well, here it is afterwards, but let's trace it out. So we start at A, and we follow pointers from A, and we can see there's a pointer to C. Okay, so C is going to be reachable, and then there's a pointer to F. Okay, and then F points back to A, and that's all the reachable objects. So we copy them, and notice when we copy them, we also copy their pointers, and now the pointers have all been changed. So in the copy of A, it now points to the copy of C. Okay, and of course C will point to the copy of F, and there's a little issue here. This line is not in the right place, so it should look like that. And then F points back to the copy of A. So we not only move the object, we move their pointers and we adjust them so that we have really copied the whole graph of objects over to the new space. Now we're using less space, and so there's some free space here. Okay, and now this will become the old space. This is now our old space. And this is now the new space, which we will use for the next garbage collection. To summarize the discussion so far, one of the essential problems in stop and copy is to make sure that we find all the reachable objects. And we saw this same problem with mark and sweep garbage collection. Now, the thing that really distinguishes stop and copy is that we're going to copy these objects. So when we find a reachable object, we copy it into the new space. And that means that we have to find and fix all the pointers that point to that object. And this is actually not obvious how to do. Right? Because when you find an object, of course, you can't see all the pointers that point into that object. So how are we going to do that? Well, here is an idea. When we copy the object, we're going to store in the old version of it what's called a forwarding pointer to the new copy. So let's take a look at what that would, what that looks like. So we have our old space, we have our new space, and let's say we discover some reachable object A in the old space. So what we're going to do is we're going to make a copy of it over here in the new space, and that's easy enough to do. But now what we're going to do is we're going to take A and we're going to reuse its space, and we're going to store what's called a forwarding pointer in it. So we're going to, first of all, we're going to mark somehow that this has been copied. So this will have some special mark on it, which I'll just indicate here with a little purple bar or something. We're going to mark it in some way so that we can tell that this object has already been copied. And then at a distinguished location in the object, we're going to store the forwarding pointer. And you can think of this as like a forwarding address. So if you know where somebody lives, you can go to their house, and if they have moved, you can ask for the forwarding address. And that's exactly, and then you can go off to their new house, where they've gone to, and presumably find them. And so that's what's going to happen here. If we have a pointer that points into this object later on, and maybe much later on in the garbage collection, we may discover this pointer. We may follow this pointer, find out it points to this object, realize that this object has moved because we've marked it as an object has moved, and then we can use the forwarding pointer to find out where the new object is and then update this pointer, wherever it is, to point to the new object. Now, just like with mark and sweep, we still have the issue of how to implement the traversal of the object graph without using any extra space. Again, when these garbage collection algorithms, they only get run in low memory situations, and you can't assume that you can build unbounded data structures to use with the garbage collector. So the garbage collector really needs to work in constant space. And here is the idea that is used in stop and copy algorithms to solve the problem. So we're going to partition the new space, and this is just the new space here, into 3 contiguous regions. We're going to have, let's start with the one at the far right. We're going to have the empty region where we're allocating new objects, and there's an allocation pointer that points to the beginning of that region. So this is the region that we're filling up with objects that we're copying over, and this is just empty, unused space. Now, immediately to the left of that region are the objects that have already been copied but not scanned. Okay, this is copied and not scanned. And what does that mean? Well, that means the object has been copied over, and so we've actually made a copy of the object into the new space, but we haven't yet looked at its pointers. We haven't looked at the pointers inside the object to see where they go. And then to the left of that are the objects that have been copied and scanned. These are objects that have been copied over, and we've also processed all the pointers inside of those objects. And so you can think of this area here between the scan pointer and the allocation pointer. This is the work list. So these are the objects that still need to be processed. These are the objects that have been copied over but might yet still point to objects that haven't been copied. And so these are the objects where we have to look at their pointers to see whether they point to something that still needs to be copied over to finish the garbage collection. Returning to our little example, I'm now going to walk through how a stop and copy garbage collector would collect this particular heap step by step. So notice that we only have one root object, and it's A. Okay, and I just want to point out that A has one pointer, which points to object C. All right, so the very first step, what we're going to do is we're going to copy the A object over to the new space. Okay, and this is literally a bit-for-bit copy. So we just take the bits of A and we do a copy without doing any inspection of the interior of the object over to the new space. And how does that work? Of course, our allocation pointer is initially right here at the beginning of the new space, and then we copy this one object over, and that means allocating an object. And so now the allocation pointer points to the first word of memory beyond the object we just allocated. Okay? Now, what happens when we copy it over? Well, because this is just a bit-for-bit copy, all the pointers in A still point to the objects that they pointed to before, which are the objects in the old space. So notice now that this copy of A points to the object C in the old space. The other thing we do is we leave a forwarding pointer in the old copy of A. So we mark A as having been copied. That's why it's grayed out. That indicates that this object has already been moved. And this dotted line here indicates that somewhere in A we've stored a pointer to the new copy of A. And now we're ready to begin the algorithm. So notice that we have some objects here that have been copied but not scanned. So this is our work list. So now we're just going to repeatedly work off of those objects. And how do we know there are objects in there? Well, we just compare the scan and the allocation pointers. So if they are different, if there's an object in between the scan and the allocation pointers, at least one object in between the two, then there's work to do. There's an object that needs to be scanned and possibly resulting in more objects being moved and allocated. So what happens next? So we process A, so we walk over A and find all the pointers in A, and we copy any objects that A points to that haven't already been moved. And so before we said, this copy of A pointed to the old copy of C. So now when we discover the C object, it hasn't been moved, it's still in the old space. So we copy it over and we update the pointer in A to point to the new copy of C. Now, of course, and then the scan pointer moves over A. We've scanned all the pointers in A, all right? And the allocation pointer also moves because we had to allocate space for C. And of course, C is just a bit-for-bit copy of what was in the old space. And so any pointers that it has that point to objects that haven't been moved yet just point back into the old space. So in this case, the object C points to the object F in the old space. And I probably should indicate here's the original dividing line. This is the old space over here, and this is the new space over there. All right, and then finally, we mark C as having been copied, okay, as having been moved to the new space, and we left a forwarding pointer to it in case so we can fix any pointers that point to C that we come across in the future. And now we have to continue scanning objects that have been copied but not scanned, and we can see that there is an object between the scan and the allocation pointer, namely C. And so we'll now process all the pointers in C. Next, we scan C, and we discover that it points to F, which hasn't been moved yet. And so we copy F over into the new space, and we update the pointer in C. And now C has been copied and scanned. Okay, so the scan pointer moves past C. And of course, F again is a bit-for-bit copy, and so all its pointers into old space are still pointing to old space. In particular, F points to A, and the allocation pointer is moved again because we moved F. All right, and now we have to process F. And this will be the last object that we move. And what happens? Well, we discover that F points to A. Okay, and A is already marked as having been moved, and it has a forwarding pointer. So instead of copying A again, we simply update the pointer in F that pointed to the old version of A to point to the copy of A. Okay, and so now F is completely scanned. All the pointers in F have been processed. We didn't allocate any new objects, so the allocation pointer didn't move. And now the scan pointer and the allocation pointer are equal. There are no objects in between them. And so our work list is empty, and this is the garbage collected heap. This is a complete graph, a complete copy, I should say, of the graph of reachable objects from the old space. So now we're done, and we simply swap the role of the new and old space, and we resume the program. So when the program starts running again, it will allocate out of this area, okay, beyond the allocation pointer until it fills up what is now the old space, right? And then this will be the new space that will be used for the next garbage collection. Here's a pseudocode algorithm outlining how stop and copy garbage collection should work. So while the scan and allocation pointers are different, remember we keep running until the scan pointer catches up with the allocation pointer and they're equal. What we're going to do is we're going to look at the object that is at the scan pointer, we'll call that object O, and then for every pointer in O, we're going to do the following. We're going to find the object O prime that pointer points to, and then there are two cases. One is that there is no forwarding pointer. All right, and if there's no forwarding pointer, then we have to copy that object to new space, and that'll involve allocating a new object and updating the allocation pointer. Then we're going to set, and here it says the first word, I really shouldn't emphasize the first word, set a word. So it's a distinguished word, that's what's important. We have to know which word we're going to use, and it will always be the same word. But anyway, we set a word of the old object to point to the new copy. We mark the old object as copied, mark old object as copied. Okay, so that's so we can tell if we ever come to a pointer to it again, we know it's already been moved. And then we change P the pointer to point to the new copy of O prime. All right, so if there was, that's what we do if there's no forwarding pointer. And if there is a forwarding pointer, then we simply update the pointer to point to the same place as the forwarding pointer. And we just repeat this loop over and over again until we've scanned all the copied objects. So just as was the case with mark and sweep, when we scan an object, we have to know how big it is, and we also need to know where the pointers in the object are. So if we think about this for a minute, let's say we're scanning this object, so this is our scan pointer, and we want now to process all the pointers in it. Well, we have to know where the pointers are. So there's a pointer here, and there's a pointer here, and we need to be able to find those pointers, and we don't want to confuse them with other fields of the object that might look like pointers. So the bit pattern for an integer could look an awful lot like a pointer. Now, this is not a big problem because the compiler, of course, determines the layout of the objects in the heap, and it can store that information somewhere, communicated to the garbage collector, so that it will be able to find the pointers. And so you can imagine easily a little bit of information stored with the program, indicating for each type where the pointers are. And similarly, once we scan this object, we need to be able to advance our scan pointer just past the object so that we can find the beginning of the next object, and that's why we need to know this size. Okay, so we need to know that size so that the scan pointer can be moved past the object and we can find the beginning of the next object. Another issue is that whenever we do a garbage collection, I haven't mentioned this up to this point, but it should be clear, we also have to scan and copy objects pointed to by the stack. And we also have to update pointers in the stack. And this can actually turn out to be kind of an expensive operation with stop and copy because you still have to walk the entire stack each time you do a collection in order to make sure that you've copied all the objects pointed to by the stack. To conclude, stop and copy, I think it's fair to say, is generally believed to be the fastest garbage collection technique. Certainly I believe that variations on stop and copy are the most efficient approaches known to automatic memory management. Allocation is very cheap, all right? So because all you have to do is increment the heap pointer. So you're just moving a single pointer forward to allocate space. There's no complicated free list to traverse or decisions to make about where to put the object. You're just going to allocate it directly at the allocation pointer. So this part of memory management is very inexpensive. And at the same time, collection is also relatively cheap. And interestingly, it's especially cheap if there is a lot of garbage because we're making a copy of the reachable objects, stop and copy only touches the reachable objects. It does not, in particular, does not touch the garbage. So if you think about that for a minute, that means that a garbage collection in stop and copy is order the size of the live objects. So whatever the subgraph is that you're copying, that's the cost of a garbage collection. And that's in contrast to mark and sweep, where the cost is proportional to all the memory that you're using, because you have the sweep phase where you have to go through and touch every single object, whether it's live or garbage. Okay? And so if you have a relatively lot of garbage and a relatively small set of live objects, stop and copy is actually much, much faster than mark and sweep. Now, of course, the downside of stop and copy is that it moves the objects. And some languages, in particular C and C++, can't allow you to move objects because the address in which an object lives is actually visible, exposed in the program, and is part of the semantics of the object. And so there, you really have to use mark and sweep because you're not allowed to move anything.